working at Cornell University and then at Bell Labs. And he came back to France in '94 when he was appointed as a professor at Université de Picardie, Jules Verne in Amiens. And in 2014, he was appointed a professor in Collège de France, and where he's in charge of the chair of solid-state chemistry. Jean-Marie Tarascon is one of the leading scientists on materials for energy storage, in particular batteries, and he has received a number of awards and prizes, and he's a member of the Academy of Sciences, and he received the CNRS Innovation Medal, the Prix Balzan, and most recently, 2022, he received the CNRS Gold Medal, which is the highest scientific distinction in France for all fields. And maybe we just move on to the presentation. And the title of Jean-Marie's talk is Materials-Electrolyte-sensing Innovations Towards Improved and Sustainable Battery Chemistries. Thank you.
Okay. Okay, thank you very much, Patrick, for inviting me to come to ESRF. I think I came here about 6 or 7 years ago, and it's a pleasure to come back and to see that things have been evolving quite a lot, and I will mention certainly some during my talk. So today I will be talking about materials, electrolyte, not too much, sensing innovation in order to improve batteries. So to start with, I will put the topic in the context, and of course, why we are working on batteries is simply because we want really to use renewable energies. As you can see in all the media by now, you have always highlight dealing with the sun, wind, and so on. So unfortunately, this kind of technology are intermittent. So you need to kind of smooth, I will say, this power fluctuation. And to do this, we need to do storage. So I think the best way to do storage that I have in my mind is simply capture here. How this stuff works, more or less, when the wind is blowing or when the shine, because the sun is shiny, you have enough energy to bring water into this reservoir. And then, once it's done, the energy here, when you want to take a shower, you just turn the faucet on and you can take the shower. And I think you have a large diversion of this kind of setup, which is really practical this time, is a kind of hydro pumping project that is in the north of Chile, where they are taking advantage of a 600-meter reef, and we have a solar plant at the top of it that is producing electricity to feed the turbine that are going to pump water on the storage, and you can have here a huge daily storage. And what is interesting is the cost of this kind of storage that is very low, but unfortunately, you have only a few geographic sites that can enable you to do this kind of stuff. So what we are going to do today is to look at a different way to store energy, which I will say is the convert chemical energy into electricity using the classical device that we know nowadays very well, that are the batteries. And the batteries are what we are going to be talking today about it. And you have several types of batteries, as indicated here, where I put the energy density as function of specific energy. And out of this technology, there is one that coming out or pop out is the lithium-ion technology. And definitively, this has been the biggest advance of the last century. And it's on why these 3 gentlemen, John Goodenough, Stan Whittingham, and Akira Yoshino, received the Nobel Prize in 2019. So today, we are going to talk about lithium-ion batteries. We'll go into some type of chemistry, namely in terms of materials. So the way that these batteries are working, schematized here, where you have 2 electrodes immersed in a non-aqueous electrolyte, where you have as positive and negative electrode interconnection compound, which are a sponge with respect to lithium. So the kind of curves that we are used to do in the laboratory at the labs are this kind of voltage capacity curve, where here the surface between the discharge curve is what is very important, is energy density, and you want to have this as mass as you can. And then this energy density is controlled or is governed by the simple relation, which is a voltage multiplied by capacity. And this voltage is really depending on the band structure of the materials, And I will be talking quite a lot today on these aspects. And then you have the capacity, and which is nothing else than the ability of the crystal structure of the material to accept lithium and kind of vacancies or oxide. So this is more or less what is very important. And also when you talk nowadays about storage system, another parameter that is very critical is energy efficiency, which in this case of lithium-ion battery, which makes this technology great, you can reach about 98%, which means that you don't lose too much energy when you are charging and discharging. And this is more or less a great asset of this technology. So now, do we move too much more in details? How is the way to prepare this type of technology in terms of materials? And the electrode performance is going to be function of several parameters, which are material composition structure, material texture morphology, and the material surface consolidation. So you need to chemically design new materials, and I think this is a work of solid-state chemists. You need to then play with the particle shape, the porosity, and we can do this via soft chemistry. And finally, you need to do surface engineering in order to control what will be the surface or the active site or your particle and so on. And of course, in all these aspects of the research, you need all the time characterization, and I will come back to it very shortly, where all these kind of synchrotron, beamline, and so on are very useful. So as you can see, the battery business, to a certain extent, is very simple. You want to develop battery, you have three pillars that are materials, interface, and devices. And this is going to require expertise in various disciplines, in organopolymer chemistry and solid-state chemistry, as well as in surface science. And then, as I mentioned, you need to characterize all these kind of electrodes. You can do it electrochemically by in situ or operando characterization. And of course, the synchrotron beamlines and neutron source are constantly used in our business. You don't worry, I will not even sometimes mention it, but most of the data came from some of these experiments. And of course, behind all of this, you need to have a theory to provide some guidance on how to design new electrolyte and new materials. And I think the field of lithium battery is very enjoyable, because here you can have fundamental scientific challenge emerging from concrete technology. And you can really get some breakthrough by doing this kind of research, and it's a run one I will try to illustrate to you. So today, what I'm going to do, finally, is to show you a little what is the science and the innovation involved toward better batteries. These are the kind of two topics that I want to handle, where I will talk about material design, novel concept. I will not talk about solid-state battery today. And then I will move to battery sustainability, where I will show you more or less the development of smarter batteries via sensing functionality. And you are going to see, in both of these, as a matter of fact, parts, we are going to have a very strong interaction of light with matter. But in one point, you will need to have a large instrument, and a second one, you don't care about large instrument. You will see more or less what type of information you can get and what are the value of this information. So let me start first by how to increase the battery energy density. So the energy density of a battery came from electrode material. So here, I'm more or less showing you all the different type of compounds, history-wise, that has been studied, starting with the chalcogenides, moving in 1981 to the lithium cobalt oxide, then to the three-dimensional compound, the spin alpha, lithium iron phosphate, and then we reach the stage of layer compound derived from lithium cobalt oxide, NMC, with nickel rich and so on. So today, commercially, all these three types of material are heavily used at the same, I will say at the same level. Lithium iron phosphate is coming back into the scene and is at the same or very soon level as NMC. And there is also another class of compounds looking at the future, which are a large amount of promise, which we call this lithium rich, or you will see later ionic redox. And this is really what today I am going to show you how we could bring these materials, where you can see, which is a capacity of 290, which is about 40% or 50% greater than the material that we have today. And more specifically, we have 1,000 watt-hour per kilogram, which is near 2 times that we are using today. But of course, we have issues. So what I'm going to do today is show you more or less what is the science behind it. And these kind of materials, as you can see here, we call them lithium rich because they are layer compounds, but which is lithium, this kind of brown ball that is you can find also on the metal layer. So we are going really to look at these type of materials. And I should say this type of research, I as rekindle the big use of spectroscopy from synchrotron beam line. Indeed, to prove this concept of ionic redox, we first have been using XPS or hard XPS, where you are looking at materials, lithium-rich phase, as indicated here, and we have been looking by XPS by changing, I will say, the intensity or beam intensity, going from 1.5 keV, 3 keV, and 6.9 keV, and we are able, in this case, to spot this peak that was assigned, in this case, to this ionic redox. So when you charge the compound, when you are the charging state, 4.8 volt, you have this type of species that is our ionic species that are oxidized, and you can see when you discharge, these species are disappearing, which means that in this case, we have a reversible process. Then, after, the technique that has been extremely used and very popular nowadays to look if we have ionic redox is what we call the RIX, where we do RIX as oxygen KH. And you can see here what you are charging the materials. You have, in this case, the appearance of sharp and bright spot, as you can see here on the spectra of absorption emission, which is an indication of ionic redox N2U compounds. Then the detailed explanation of what this spot is and how it forms and so on is still questionable. So this is a way more or less that these materials have been identified and are identified today. So finally, this more or less was the situation 25 years ago, or for 25 years at least, the community was believing that the way to get capacity from the compound is solely based, as you can see here, in the cationic redox. And this is more or less the materials that we have been using with having capacity of 150 to 200 milliampere per gram. Now, what we have been showing since about 2013, 2014, that this stuff is not any longer true, since when you are oxidizing, you see the cations are giving electrons, and then when you go to higher potential, you are able to tap electrons from the oxygen network, which means that in this case, we have an increase in capacity, as you can see, nearly a doubling of the capacity. So this is more or less what we have been demonstrating. And of course, what is very important is to know what is the science behind it and how this happens. So in order to know the science of this type of paradigm, you need to go back to the electrochemical potential of an interaction compound that is really governed by its electronic structure that itself depends on the composition as well as on the structure of the material. So if you look at the structure of these materials, you have the classical lithium cobalt oxide compounds, where in this case, each metal is surrounded by free oxygen, and all the doublets of the oxygen are taking part of the process. And in this case, the band structure is simply nearly an overlap of the 3D metal orbitals and the p orbitals that result in a 2 bonding and anti-bonding orbital, with one having a strong M character and one having a strong oxygen character. And this is a classical cationic redox process, where when you oxidize, you are removing electrons as indicated here. Now, if you look in the case of these lithium-rich materials, here, look now, you can see that only 2 doublets are participating to the bonding. You have the next one that is really pointing to our lithium, which is very ionic bond. Is one why we consider this doublet as a non-bonding doublet. And this non-bonding doublet is going really to position, as clearly indicated on the band structure, above the anti-bonding, above the bonding, I will say, orbital. So in this case, when you are adding oxidized compound, you are removing electron from a 2 bond, the non-bonding, as well as the 3D metal or metal oxygen bond. So this is more or less the occurrence of this 2p oxygen bonding that govern the ionic redox. So these are these kind of materials that I told you are very interesting from application, since they offer a large energy density. But however, you need to realize that when you want to do for practical application, the energy density is only a single figure of merit. And you have some drawbacks, namely the voltage fade. But here, you have what you can say the large hysteresis. In the large hysteresis, you remember what I told you on the third or fourth transparency, means that you cannot have high energy efficiency. So the rest of this part on anionic redox is going to show you more or less the research that we are going today in order to at least overcome these difficulties. So you look at this hysteresis, you have plenty of lithium-rich compounds, and you can see here the hysteresis is changing quite a lot, going from iridium phase to the tungsten base. And what is changing here? The hysteresis increase, but also, I will say that you have, in this case, a decrease of the covalency. So you have a kind of relation between the hysteresis and the covalency, and our goal now is going to see more or less what is finally this kind of role of this non-binding state, the role of the charge transfer from these oxygen non-bindings onto this kind of voltage fade. So to do so, we are going really, in this case, to see what type of mechanism it is. So when you look at the literature, we have been, at the first time, claimed that we are, in this case, this type of reductive coupling, which means that you can see here, we have, in this case, an electron that is leaving from the oxygen that is going to reduce the ruthenium, and you have ruthenium plus side. For those who have been working on superconducting materials, this is more or less the same thing that do happen with ITC material. Then other groups have proposed the same thing in the case of manganese, where in this case, again, you have this kind of reductive coupling or ligand to metal charge transfer. The same thing in some recent compounds that we have been working on, where in this case, we found that we have iron plus 4, iron plus 3. But the question is, we claim that we have this ligand metal charge to metal charge transfer, but we never experimentally observed. So the question here was, how can we design a compound in which we could finally capture this ligand, which is LMCT, I will call it from now, into these materials. To do so, we have been really trying to design new compounds, and we work on this kind of layer type material, lithium, nickel, titanium oxide. By doing this, we took different types of composition, and I just present one here, that is lithium 1.17, titanium 0.58, nickel 0.2502, where in this case, we get pure phase, which we are, in this case, the type of cation disorder, rock salt structure, where we have really a cubic structure, and which, in this case, we have all sites occupied by nickel, titanium, and lithium at the same time. And when we look at this type of materials, this is more or less a type of voltage composition curve. And you can see it's very strange. Now, what is happening is when you are really oxidizing the materials, and here you have nickel plus 2 to nickel plus 3, all these informations are coming from exact measurement done at synchrotron beam lines. Then after, we have oxidation of the O2 minus. And then on discharge, you have really nickel that is reduced and oxygen that is reduced. And for people that know a little electrochemistry, this is a very counterintuitive. It's the first time that you have really the peak in oxidation doesn't come back first on the reduction. What means in this case, we have what we call this redox immersion. And to clarify this point, I just put here a simple cyclovoltammogram where you can see I oxidize my cations, oxidize my anion, and theoretically, when I reduce, I should reduce the anions and then the cation. But here is opposite. So the question is going to be now, why and what happened? So in order to understand this, we do kind of classical measurements. We do in situ XRD, and we are going now to plot what is happening on the variation of lattice parameter A as I am going to charge and discharge my cell. So here the full square are during the first charge, and the open are during the second discharge. And what you can see in this curve, again, is drastically different you should expect that everything match each other on charge and discharge because it's reversible. It's not, because you have a structural hysteresis. And then you are, in this case, operating in a non-equilibrium path. And the question that he asks is, how can we move from this non-equilibrium path to the equilibrium path? And do we go to intermediate state? The experiment to do here is, to a certain extent, relatively simple. We just look at our sample, we charge completely, means that we are at the end of charge, and we leave it on relax. And we monitor X-ray when we are nearly relaxing. And what we found, without any current at all, just on discharge, we have a shift of the black peaks, which indicates that something is changing into the compound when you are relaxing. We can do it this daily in electrolyte, and here we were very concerned because we have a self-discharge. We decide to do it out of electrolyte, and here, again, some referee were contesting. We are obliged really to move to solid-state batteries in order to do this experiment and to really show that indeed we have this kind of relaxation. And what is happening is we have this kind of structure, and if we have, in this case, a shortening or an increase, excuse me, of the bond length, which means that we are creating more nickel plus. Okay, and this was already the first evidence that we have this kind of charge transfer. It means that electron is given to nickel, which in this case, nickel is reduced. So the question is now how we can quantify this stuff better. So here we did similar type of relaxation experiment, and which we clearly follow by electrochemical titration and expert characterization. So I put this kind of scheme here because it's very important to understand the experiment. What we have done here, we charge a cell, we recover the powder, then after we relax the sample by heating. So it means that we are going to the sample at 50 degrees, 80 degrees, 100 degrees C, and then we are going to relax for 24 hours, and then we are going to bulk fresh cell with this new sample. And what you can see is as you increase temperature, which means you increase the kinetics, what you found that you have this kind of transfer of capacity from the high voltage to the low voltage, which means that in this case, as you are relaxing, you are nearly pursuing the charge transfer, and you create more nickel plus 2, so that more or less you end up without too much nickel plus 2. And we can see this very well in the derivative, where you can see the nickel reduction peak is decreasing, while the oxygen reduction peak is increasing. Now, if you really want to convince people, you just do, in this case, experiment the nickel 2p and oxygen 1s. And this is a kind of sample during relaxing. And you can see that the amount of nickel plus 2 in green here is increasing as you are waiting, which means that you are reducing. At the same time, both N minus is increasing, which means simply that you are, in this case, doing the charge transfer from the oxygen to the nickel. So by doing this, we can more or less kind of recapture what is happening into this kind of compound. When you do the electrochemical curve, you are oxidizing, in this case, both nickel and oxygen, and you get this kind of nickel plus 3, nickel plus 4 intermediate. And then when you are reducing, you reduce the nickel intermediate and as well, and the peak that you're observing. So what does it mean? Is in the case of band structure, this is more or less my band structure, where I can define what are the level position by DFT calculation. And when I am oxidizing, what is happening? I remove first my electron from the nickel 3D state, and I get a long life metastable state. And what happens here after? Ideally, have a charge transfer through this nickel state. And why? I should go back one point. Why I remove the electron from nickel state at first? Because the kinetics are quite faster from the cationic than from ionic redox. So this is more or less what we have been finding. So the question now that we may ask, don't forget, I told you we have a cation disorder rock-salt structure. And you may wonder what happens if we do more classical layer compounds, which are ordered. And this is more or less the case of lithium, manganese, nickel. And it is a case of this layer, NMC, that lithium rich, the first one that I mentioned. And you can see here that you still have the same phenomenon. So here again, why we are able to spot or capture this feature, because we are able to create a long metastable state. But even in very highly covalent compound, you have the intermediate state, and I think maybe it's up to you to find the spectroscopic technique to go to pick it up and so on. And as a matter of fact, this is a European program that we are running now. We just started in order to see if we can visualize the electron like we visualize the atom and the kind of chemical reaction. So now you can say, fine, so how this stuff is useful? How this stuff is useful because when you look at this kind of hysteresis, it does exist in the classical lithium-rich NMC that we are still not commercializing because of difficulties and overcoming this hysteresis. And so now the question that I can ask, can I decouple what will be the effect of cobalt or nickel on this charge transfer? And to do so, here again, we need to go back to classical chemistry and prepare new material. And this is the type of compound that we have been making. You see, we have a very complicated material, okay, and we decouple. And we make these two compounds. Here are the voltage composition curve. And the voltage composition curve, again, by spectroscopy techniques, we know that we have a cationic and anionic. And look already here, difference is that in the case of the cobalt, look at the cationic part. It's relatively limited, while the anionic part is quite more important. And you will have more. And of course, when you look at this material in the fully charged state, and if you look bricks, you have this magic bright spot that came out, indicative of this anionic redox. Then you look at this material for other properties. You can see that in the case of nickel, you have a kind of good performances with respect to the case of cobalt and so on. This means that the nickel redox is more important and the oxygen lost is less important and so on. So from this experiment now, when you are really building lithium-rich NMC compound, we demonstrate that at least nickel is better than cobalt. So question now is, we know this and how we are going to design new materials or we are going to solve this issue. So to recap, what I am telling you so far is indicated here. We have this hysteresis that is really due to ligand metal charge transfer. We have the electron from the oxygen that are electronically limited, kinetically limited, and we have the one from the cations that are favorable. So what happened is you have this simple charge transfer to a certain extent, what we found a long time ago in superconductivity. And question is now how you can really overcome it. So you can overcome by going to different type of elements and which more highly covalent. And of course, you take ruthenium. Here you have a very highly covalent material, iridium, and here you are going to limit your charge transfer. But when you go to iron, nickel is increasing. Then you want to have a more covalent material. From a chemical point of view, you simply go to the periodic table and you move really from oxygen to sulfur and to selenium. And lastly, you can really now go back to the oxide and try to balance better the cationic and anionic redox. I will briefly show you these two approaches very simply. But indeed, when we move to type of chalcogenides, this is the type of materials that we have been making. Indicator here, lithium-2 TS3, which by the way is the equivalent of lithium-2 MnO3, and which by doping with iron, we can trigger the anionic redox. And in this case, we obtain these kind of materials with relatively small hysteresis and so on. Now again, when you look at XPS, you found that indeed, in the fully charged sample, you have this kind of two peaks associated with this oxide sulfur. And I should say here, for people with spectroscopy, the basic understanding behind this peak today is not known. There is a large amount of controversy on what is a dimer and so on, because we have made compounds in which we have dimers, in which we have the partially oxidized sulfur, and we always get the peak at the same position. And here again, another challenge is up to date, to my knowledge, no one succeeds in making rigs as a sulfur carriage. So this is a type of materials that we are also working with. So indeed, you compare this compound to the case of oxides, you can see that we are, in this case, having a great advantage in terms of efficiency. As you can see here, we moved nearly from 87, I think somewhere here from 95. We have no irreversibility and so on. So I think here we have other types of materials that may present an interest in the future, owing to their performance and more specifically in the case of solid-state batteries. And indeed, we have nearly look at these materials in the case of solid-state batteries. And here, I think we get very good performances, where you can see the very small hysteresis, look at the cycling that we can obtain, and nearly the kind of power rate. And I should mention that this experiment has been done versus lithium metal without any polymer, without any liquid, and again, at relatively low pressure, about 10 megapascal. If you look here and what you can obtain, if you compare to the kind of NMC in terms of solid state, because one other advantage here, since this compound is a good mixed ionic and electronic conductor, I don't even need to use argyrodite as my additive as a positive electron material. So this more or less to tell you that this type of material can be highly competitive to oxides to make nearly solid-state batteries. So this was the first point that I want to mention to you. The second point that we have been working on, and I think is going to relate it to one poster that I showed this morning, is finally, let's go back to this kind of quaternary diagram. And this is more or less what people have been working on this NMC system for the last 25 years. Large amount of work has been done, number one, on these NMC compounds, and this is more or less the one that you have nowadays into the market with the SEX2 and so on. Then people have moved along the tie line, as indicated here, and you reach this kind of lithium-rich compound. But there is interesting in the diagram, you can see that no one bothered to explore this kind of rich compound in nickel. And this is more or less this kind of materials that we are going to use now. So what we are going to do now, try to prepare new compounds in which we are going to insert, or I will say a lithium-rich compound into lithium NiO2. And to do so, we are going to use this type of chemicals. We can use manganese, but there is other type of derivative using titanate, niobium, and molybdenum. And what we are going to focus is on this type of composition using molybdenum. So here we have been doing the synthesis, and this is more or less a waste that has been made. We made this stuff, I will say, by kind of solid solution that we fire then at high temperature. And you can see the X-ray powder patterns, as you can see here, for lower composition, looks like the X-ray powder patterns looks nice, great. Unfortunately, we did TM, and when we look at TM, we found that the samples were not single phase, but they were kind of made of integrals of layer and disorder type material, with the layer being kind of lithium nickel oxide type structure, and disorder being kind of lithium-4 MO05 structure. And this enabled us to explain one interesting feature in the X-ray powder pattern that we could not explain at the beginning, which is the change in intensity of the 003 and 104 peaks as you are doping with molybdenum. And now, having this kind of information, we can nicely fit this X-ray diagram using two types of structure, the R3M associated with the layer compound and the F3 Fm 3 - M as daily lithium-4 MO4. So when you look at these materials then electrochemically, what is interesting, you find the same type of feature that in the classical layer compounds. And what very important here, if you look at the derivatives show very sharp peaks. And this is a clear indication that we don't have daily doping within the material. Because you take nickel oxide and you dope with cobalt, automatically you have a broadening of it. And if you look at the performance, as indicated here, you can see that this composition here is the one that really shows the better stability. Question, why? So why? This is our explanation. It's more or less what we have in our materials. Finally, we have a composite of layer compounds with nanodomains of this kind of phase, lithium-4 MO5. And what is interesting, if you look by TM at the interface, we have a coherent interface. And what we believe is simply that the mechanical strength energy associated to the lithium intercalation or the intercalation is compensated by the epitaxial energy associated really to this coherence interface. So this is more or less a way that we explain what is. So to make the story short, I think this lithium-rich and nickel-rich are a new playground for high capacity and high stable electrode material. So this is more or less what I would like to conclude my first part dealing with material science that we are doing. And where we have been using quite a lot, even so I didn't show you many data about this kind of synchrotron beamline experiment and so on. So now I'd like to move to the second part that is going to be as new, is dealing with how to increase battery sustainability and diagnostics. So here the story is how we can develop smarter batteries. So if you want to look at diagnostic, and I have a very nice discussion this morning, you are doing this stuff very well here at the cell level. So it means that the X-ray tomography of lithium batteries has been pioneer, I will say, by Vanessa Wood. Maybe I'm not an expert per se, but I think it's my knowledge. And but I think a large amount of progress has been made. Luckily, because as you are here, we have high photon plus fast detector technologies that enable you, more or less, to go now into very deep details, looking at structural defects occurring during the cell operation. In parallel, but even earlier, people have been using neutron in order to do neutron radiography, in order to do the lithium repartitions. And now, by coupling with tomography, people are able to determine what is the absorption density and what is finally the lithium distribution into an electrode and during aging and so on. So all this kind of stuff enable you, and I think you are doing it very well, to get insight on the electrodes, degradation mechanism, and diffusion kinetics. But this is great, but we can do better for practical application. Why do we need to do better? Because if you look today, I think as a research lab, we have been very good in developing, and not we have been, people have been very good, not me, in developing operando techniques in order to look at what's going on into the battery, even really spotting the SCI and so on. Okay? But the question is, when you look, we are talking about it this morning, all the techniques are developing here at the cell level. The question is how you are going to transplant to the system level. And today, we have a big gap between all what we know at the cell level and all we can access, target at the system level. And this is more or less what we are going to try to do today. So like, the question is how to anticipate the failure in integrated systems, which metrics should we monitor and why? So why we need to do this? I say we need to do it, and today content. Everyone wants really to have a longer battery. Everyone wants to give a second life to the battery. Now, with the increased renewable energies, there is also a need for development, another type of technology that we call V2G, where in this case, you can connect your car to the grid when you are not using it. You can send back electricity to the grid or vice versa. And this, you do calculation, you have a huge amount of energy that you can store. We talk about 5 to 8 terawatt per year, assuming that we have 40% of electric vehicles by the year 2030. And then also, we need to have a better use of today's batteries, because electric vehicles, because of the lack of mastering this kind of physical parameters, we are not fully using all the possibility of the batteries. We are limited to about 70 to 75%. And nowadays, as a matter of fact, the only metrics that you have here, you don't even have a temperature in a single cell, you have temperature in a single module. So definitively, here, we need a better traceability to establish the battery health status alike for human beings. Question is now, how we are going to do this? To do this, we are going to get inspiration from the field of medicine. You have the idea of operation. What is happening? The surgeon is putting optical fiber and try to transmit information from the inside to the outside of the wall. The idea behind it, all this work, has been, can we duplicate it? Can we implement the same thing at the battery level? And this is more or less what was our dream long ago, 4 or 5 years ago. So to do this, we need, of course, to inject, I will say, some smart sensor into the battery, some optical, acoustic, and finally, what we have decided to use is optical fiber. Why we decide to use optical fiber? Interaction, of course, light matter, but because they have several advantages. Number one, when you are working with a battery, electrical system, optical fiber are insulated. And second point, they enable multiplexing. And multiplexing is going to be a huge advantage that we are really to try to get out of this. So more or less, we are going to use this fiber drag rating sensor. So what are these sensors? Very simple. You take classical optical fiber, and what we have, in a limited range of the fiber, you have really a periodic variation of the refraction index of the fiber. So that when the light is going to go to this fiber or to this sensor, it's going to act as a mirror, and it's going really to send back a light as a special wavelength that we call lambda. And of course, what is very interesting is that the spacing between this grating is going to affect the position of this really peak. Which means in this case, it's going to change with temperature, as clearly indicated here. And this is more or less what we are going to see, because it will change with temperature, pressure, and strength. So what we are doing now, we take normal cells. You have here a pouch cell in which we put the fiber, or an 18650, in this case, made of the sodium-ion technology. And we put the cell inside. And what we are doing to do is really to monitor what is happening here between the inside of the cell and outside the cell as functions of the rate. And here you can see different C rate. And you can see that I rate, you have a large difference between the inside and outside. Again, since we are multiplexing, means that I can put several sensors along my fiber. And if I do this, this is more or less what I have here, where now you can see I have the 3 fiber, and I can get all variation temperature gradient around the y-axis. And you can see the difference that you have between, in this case, the top and the bottom sensor. Means you can get temperature gradient in the basal plane as well as in the vertical plane. So then you can get this kind of temperature, measure temperature, but temperature is certainly limited. We want to go one step further. Temperature is heat. And of course, heat is chemical reaction. So we need to go here from this temperature, convert them into heat. So this is more or less what we have been doing by, in this case, using a thermal model or an equivalent circuit, in which in this case, the capacitance are the heat capacity, and where the resistance are the inverse of the coefficient, heat coefficient transfer. By doing so, we can obtain this type of formula where we have now description of all the heat associated to this. And this, more or less, is we have made a new optical calorimeter in which we can have access now to the heat release during the type of reaction. And of course, this has been used, of course, to design efficient cooling systems. So now, this is fine. Now let's see more or less what is happening also. We can now have access to the SCI layer. What I am looking here is a sample voltage charge curve. Okay? And I measure here with my sensor all the change in temperature as I am charging myself. You can see we have a huge peak here, huge release and energy and heat. And this is more or less signature of a chemical reaction. And then you have the different most small peaks associated to phase transition. So this peak looks like is a SCI formation. But the SCI, we should remember, is coming from a chemical decomposition of electrolyte and so on. We have a temperature increase, but you have always some gassing. We can also measure the pressure. In this case, we change the type of fiber. We put a microstructure optical fiber. And you can see now, look, I monitor the pressure during charging, and you see, bingo. When you have the release, this kind of chemical reaction, you see a huge increase in pressure. We're telling you that indeed, we are really spotting the SCI. So here we have nearly a new way, I will say, to very highly and rapidly bench new type of electrolyte. And people now, of course, they are excited about this technique to determine this kind of SCI heat. Now we show you an example where here I will take three types of layer compounds that you know very well now, some of you, this 532, SEC22, and 811. And what we have been doing here, we make some cells and we measure the heat associated to the SCI growth of this different type of cell. And what we found is indicated here. You can see the Q, the heat. You have the area in the case of 532, you have a kind of single peak. You have two peaks in the case of SEC22 and L1. Then you can integrate this peak, you calculate the integrate heat, and you can see that the total heat is lower from NMC 532, SEC22, and L1. And this is exactly what you have when you are cycling the cell. As you can see here, you have the same sequence. And we know that the heat is less in 532 because in this case, the electrodes are monolithic and you can really control. This is more or less one way that you can really get the parameter into the material. Then another way is now to measure the strength or the stress within the electrode. Because I show you that the sensors are reacting on temperature, but now you try to extend the fiber, compress the fiber, the same thing, you will change the gradient and you will modify the wavelength. So you can now put this fiber into electrodes and, of course, measure the stress or the stress field within the electrode. And of course, the electrode that we have selected is a silicon electrode, as clearly indicated here, because we know that the volume of the electrode is changing by 300% during the intercalation. And when we do this kind of experiment, this is a way that relatively simple. You take a switch load and we put the fiber within the silicon electrode, and we measure finally the answer, what was the result when you are really cycling the cell or reducing. And you can see we have in this case a different kind of strength, depending we have a nano or micro silicon. And this is the thing that we are trying to implement right now in solid-state batteries in order to know the stress repartition within the stack and so on. So now I show you more or less kind of physical parameters and thermal parameters. Now the question is, something is missing very highly. What is the chemistry of all these species? So now you need to change the concept. Now if I have an optical fiber, as I use it, I use a single mode optical fiber with a core and a gate. So it means the light is going through the core. Now, if I want really to have access to the chemistry, this will not work. I need to have a multiple fiber, and I want the light to have access to the outside. So what we do is really we use this kind of tilted track fiber grating, where in this case, as you can see, we start to take advantage of the evanescent wave that propagate as an interface between the electrolyte and the surface of the fiber. And this is, again, well known. We have not discovered this because this has been used in the past to determine what is the concentration of sugar and water by just measuring the refractive index as indicated. Anyway, so we can do this kind of stuff. And then, of course, we can implement in the case of batteries. And what you have here, we measure the refractive index, and we can have access to some of the molecules. But the question is, we can really determine here by refractive index what are the reaction paths, but we can still not have access to the nature of the molecule involved. So as we mentioned here, we are still blind to exact molecular dynamics. The question now was really how we can better utilize the evanescent wave and have access to this chemistry. So this is more or less, if you want to have access to the chemistry, you need to look at the vibration of molecules, you need to look at infrared or UV or whatever. And in this case, you need really to have a wavelengths that are really not within the capacity of the silica fiber. Because in the case of silica fiber, you are working between 1 and 3 microns. For telecommunication, you are working at 1.5. So now you want to look at the vibration of molecules. You are really obliged to move to different type of wavelengths in order to get, I will say, the absorption associated to organic molecules. And now, what we have found, we succeeded, is we have changed the type of optical fiber. And we move to chalcogenide fiber. These chalcogenide fibers are opening completely the window where now you can have access to all these vibrations and to this different type of molecule. And we have done this, and we are lucky because we have a very good lab in Rennes who are producing this kind of chalcogenide fiber, and we kind of match with them in order to develop this. So by doing this, now we can really have access within the battery, commercial battery of the type of electrolyte. So the experiment is as follows. The DLE in this case, you need to have a spectrometer. This is more or less a chalcogenide fiber. Okay? And here, this is more or less what you get. You can really pick up all the components of the electrolyte. So you can now follow and dynamic the chemistry of the battery. And this is more or less what we have been doing now on different types of materials, commercial cells. We are looking here at a cell, sodium-ion cell, based on this electrolyte. You can see here all the peaks that correspond really to a difference between reference, where the peak at the top related to decomposition and the peak at the bottom related to formation. And we can follow now all the different functions, the carbonyl group, the CC ring, and all the carboxyl group. And look here, what is very interesting. We found, as it was known, that during this kind of process, we generate this carboxyl. So this is more or less what we can do. Now, of course, we can also, in this case, look at additive. And here, what I am going to show you an example, an interesting example, where now we couple FBG with infrared. So at the same time, we measure temperature as well as the ionic decomposition. And you can see here the two types of experiments we are doing. And you can really collect, I would say, well-defined infrared spectrum. And to convince you of the accuracy of this type of measurements, this is more or less a pedagogical example, where now we have an electrolyte and we are using an additive. And the question is to know at which potential this additive is going to decompose and act or play its role additive. So what I am going to show here is I am taking a battery in which I will use this vinylene carbonate. And what I will look at it is really this carbonyl group. So I am going to monitor this carbonyl group during the session. And what happened? This is the charge. Now I monitor, look here, I have two fibers, so I measure the temperature. So my temperature is telling me that at this temperature, here, or this potential, I have really a chemical reaction. And then if I look at infrared, at the same time, I see that the carbonyl function starts to decrease at exactly the same point, which means that my electropolymerization of vinylene carbonate is taking place. So I can really correlate at which potential this can happen. And so now I know that we have this reaction of 3.15 volts. of course, we are knowing it before by kind of electrochemistry. And so this is more or less what we can do at the electrolyte. And then the question is, can we also spot at the electrode level? So what we have been looking at is now the optical fiber, where in this case, you can see we make a slurry, and we ideally dip the optical fiber on it so that we have this kind of coverage. And then we measure. And here we did two types of action. One is very chemical oxidation by putting this fiber into the iodine. We monitor the spectral change. And we see very fast the change from LFP to FP. We have done the same thing in the case of lithium iron phosphate, now electrochemically, where now we monitor an oxidation. This is more or less what you get. We can see nicely the infrared spectrum that is changing as you remove lithium from the material. And from this, you can integrate it, and you can really detect what is the state of charge of your electrode by really integrating this IR spectrum. So this is more or less what today we can do by using the interaction light matter in really via optical fiber. So our dream is here. It means we want really to move to smart batteries, and we want to create this lab on the fiber where we could really have, in this case, all the optical fiber, all the physical, thermal, and chemical parameters on the same fiber. Not on the same because infrared and physical parameters are a little different. Then after you have the information, we develop, I will say, smart BMS that will use artificial intelligence to get better algorithm. And the goal is more or less to determine and to establish an electronic passport of the batteries. So like that in the future, you will know when you want really to use the battery or for second life and so on, you will know exactly what is the state of health of your battery. And this stuff is not a talk, because if you look at the European directive, Europe, as they publish in stuff, they will have to have an electronic passport in 2027. I should say they are very ambitious. We are not there yet. But at least we are on the road. So this is more or less what we have been doing. And of course, we share this stuff with you. All this stuff is fine, but is it really practical? And are we going to implement this stuff tomorrow? Of course, some of you really certainly have a lot of questions with the practicality. So indeed, we are moving to this point. To tell you what we are doing, we are modest. We realize that putting sensor and all the battery is going to be difficult. So what we are doing today, and this is more or less, we are going to use the multiplex. And our goal is to put all these sensors around the battery to detect temperature and what is important here, look here, the type of interrupter. Like a defibrillator. We can really control. So this is more or less where we are going. And we are, of course, in this case, doing some partnership with different companies working, I will say, on data processing. So as you see, we are not putting yet the sensor into the battery because it will be difficult. Whatever, I think let me conclude. I want to try during the presentation at least to give you two examples where we are there going to use very strongly the interaction of light with matter. I show you more or less how, by doing so, we can design better compounds, because in all this work, I think we have been heavy user of all the synchrotron bin lines, either RIGS, either RDSPS, either SAS, and so on. We have been using stuff quite a lot. And I think this is why we succeed in understanding some of the material. And then I show you more or less something more or less less expensive in order to have information. And I don't claim at all that by doing of this kind of optical fiber sensing, we get as good information by this large instrument. It's totally different information. But I think it's more practical, and I think it's more or less both need, I will say, to work together and try to match, maybe have an idea how we can perform better experiment in your site using optical fiber to bring light. And with this, I would like to thank you for your attention.
Thank you very much, Jean-Marie, for fascinating presentations. we're going to take questions now, of course, from the room, and we also have many people on Zoom. So people who are on Zoom, you are invited to put your questions in the question and answer box at the bottom of the Zoom window, and then I can convey the question to the speaker and to the audience. Who wants to start? Okay.
Impressive talk. What is the typical lifetime actually of the lithium-rich and nickel-rich battery?
Again, this is a kind of question that we little talk a lifetime. The lifetime of battery depends more or less how you are going to use it. Okay, because you have some kind of report like Chef done is claiming that the battery will last for 100 years. If you limit more or less the range of functioning in terms of potential and so on. But I think nowadays, in terms of lithium-ion batteries, even in Tesla and so on, you can reach more than 3 million kilometers. So 10, 15 years, I think, is more or less where we are today.
Thank you. Questions? Yes, Jakub.
Yeah, thank you. Really impressive, yeah, I have to say. So when you're using these fibers to measure all sorts of physical quantities, so what is the actual effect of the fiber to be incorporated in the battery? And are you, so we, for example, measured that the beamline that when you put the collector, like the top, the areas around the top are not charging the same as everywhere else, right? So you put some mechanical disruption to the battery, and perhaps the question is what you are actually measuring, and if it really corresponds what's also happening further than you measure.
Of course, these are good questions. First, of course, when we did this kind of experiment, we did a blank test. So we did we take 2, 3 cells and 4 cells, and we did with and without optical fiber. And more or less the cells are behaving the same. Again, our tests have not been behind 100 or 200 cycles, which is not sufficient for cell application. Now, when you do this kind of stuff, what is happening, the way that we are doing it is, number one, we are lucky in this topic because we have a battery from Tiamat. So if we didn't have a battery from Tiamat, we could not have progress in this project. So we receive batteries as we wanted. They are without electrolyte. So like that, we can really fill our electrolyte and after put our fiber and we put a seal. So we don't perturb the battery. Okay? And this is the case of FBG. In the case of the infrared, they are a little more complicated because I need to pierce on both sides. Okay? And here again, we cycle about 100 cycles. But sometimes, we'll be honest, the seal is not good, we have pressure. Okay? And what also is an issue that we have not tested yet, because we are working, especially in the case of CO2, this kind of electrolyte that contain most of it, lithium PF6. You know the lithium PF6 can degrade and HF. And SiO2 and HF, you know what happened. So in case that in some we may have issue. But so far, we have not observed for at least 1 cycle. We went in temperature to 55 degrees, 60 degrees, it was fine. And we have, as a matter of fact, some cells that have been running, but we are trying to exploit it now to see, look at the entropy change, the aging. We have cells that have been running for 300 cycles. This, I think, is the maximum that we have using this sensor.
Thank you. Yes.
Thanks very much for the very nice talk. I was wondering if you can say a few more words about this multiplexing. I mean, the data you get from these fibers are very nice, but you were showing at the end that you have only one fiber that is able to measure different Bragg reflectors. How can you address different positions? Do you use different wavelengths, different spacing?
Oh, alors each sensor have its own wavelength. Okay, so it's on one more or less you can do this multiplexing. And I think this kind of small interrogators that I'm showing you, we only have 2 channels, but we can have address not 40, we have address but 20 sensors. We can address. And again, I think the issue that we have is just a laboratory scale in terms of temperature stabilization. But what you need to realize that all what we are doing, at least in terms of efficiency, there is nothing new. Because these sensors are used more or less for health monitoring, of bridge and so on. And by now, we are even working with Safran, who is really have the same issues for airplane and so on. So there is plenty of communities that are dealing with this kind of stuff, but maybe they never talk to each other. And we try to bring all these people together.
More questions? Come here.
Thanks for the nice talk. I'm impressed by the amount of work I saw in less than 1 hour. I was wondering regarding the disordered and ordered phase you showed with the lithium molybdenum oxide. Have you tried to do electron diffraction on the single phases that you see on the TEM image to confirm that you don't see the same phase on the diffraction pattern?
Yeah, no, this we tried. Yeah, we don't see it.
Okay. Okay, you don't see the.
Yeah, no, you don't see it.
Okay, because I was wondering what happens. What do you have below the background of those diffraction patterns, and if the disorder pattern could be just below the background, and the synchrotron could help in that case.
Good point. I see your point, and I don't think I cannot answer your question in this way. I need to see with our guy who's doing TM.
Okay.
I was putting on your first, but you're right. You're underneath. You may have a BLE. You may have what? You want to have a moire or what?
What?
You want to have a moire type pattern?
Yeah. With something. Yeah.
Maybe. I don't know.
Okay. Thanks.
Thank you. Any more questions from the room? Okay. So then we have also a few questions from the people who are on Zoom. And so we have a question from Ilya Tertov, who says, have you, concerning the lithium-rich, nickel-rich composite with molybdenum, have you observed the volume expansion during the cycling of the composite? And have there been any structural changes during the cycling?
Yes, no. We have looked at it and we don't see it.
Okay. Thank you. Concise answer. And then a question from Sami Vasala. Have you considered sulfur K-edge rigs similar to the oxygen, for example, at ID 26 at ESRF?
I don't know that you can do this stuff here because again, I think there are people using it. I think Stanford is using it. We are working with Guide 1. I think there is also, we have been working on the issue with Simon in Paris, who is trying to do this experiment at Soleil. But so far, if someone can do it here, you can get a sample if you want.
Thank you. Next question is from Michael Booth. Are there any inherent reasons why the application of the anionic approach to the spinel structure would be less likely to yield results you project for layered structures? Yeah. Are there any inherent reasons why the application of the anionic approach to the spinel structures would be less likely to yield the results you project for layered structures?
What final structure of what?
That's a question.
I don't know. Someone understands the question? Maybe someone want to translate? Because
no, it's spinel structure. Yeah. No, okay. So maybe the answer is we don't know.
Or maybe I don't know. A final structure of the composite, but you know, I am going to try to find out what the question to answer. It is difficult.
Okay.
Someone understand the question? I don't know.
Okay, so let's leave it open. Any more questions? Okay, so I think let's thank Jean-Marie Tarascon again for the beautiful presentation and an insightful discussion. Jean-Marie has a little time for more informal discussions if people want to ask him. Thank you. I have the Merci beaucoup. 200 personnes sur vous. D'accord. Votre article de brevet. Et on est passé devant le grand bras. Very nice.